So, good day. We are the group 4 from BS Electrical Engineering 33 from PUP. So, ang assigned topic po sa amin ay ang branch circuit and overcurrent protection and arc flash analysis. Which is yung branch circuit and overcurrent protection, yun rin po ang circuit breaker rating determination. Branch circuit and overcurrent protection. Okay, let's proceed. So, syempre, bago ang lahat, ano nga ba ang circuit breaker? So, sabi nga dito sa PEC, dinefine ng PEC, which is the Philippine Electrical Code. Sabi niya dito, a device designed to open and close a circuit by non-automatic means and to open the circuit automatically on a predetermined overcurrent without damage to itself when properly applied within its rating. So, gusto ko lang i-highlight yung part dito is yung without damage to itself when properly applied within its rating. So, kaya nagkakaroon tayo ng circuit breaker determination para makalculate natin at makita yung accurate and precise rating ng circuit breaker. So, syempre, ang circuit breaker ay may malaki ring parte, lalo-lalo na sa mga establishments, kasi ito ang nagsisilbing protection when it comes to electrical. For example, kung ang rating mo sa isang circuit breaker is sobrang taas, ang mangyayari naman nun, para nagkakaroon na ng aberya, pero yung circuit breaker mo, hindi pa rin nagtitrip, which is dangerous. Kapag naman sobrang baba naman, wala pang aberya, pero nagtitrip na yung circuit breaker mo. So, ganun. So, kaya nagkakaroon tayo ng mga calculations para ma-determine natin yung dapat na circuit breaker rating sa certain circuit. So, next. So, itong formula na to, gusto ko lang naman itong i-highlight dahil kumbaga dyan tatakbo yung formula natin, which is the IB is equals to KVAB over square root of 3 times KVB. So, itong formula na to comes from electrical design analysis, voltage drop, short circuit calculations prepared by Romel V. Alcasabas, RME, MEPF. So, ayun. So, i-take note lang po natin yung formula na to. So, kung makikita po natin sa schedule of loads ng Vista Mall, Pampanga, itong panel na to is included doon, which is one of the schedule of loads. So, pero dito muna tayo magsisimula. So, for panel PP3A, ang gusto ko lang naman pong i-highlight sa part na to is yung total connected load, which is 108,360 kVA. Tsaka, syempre, ang 400 volts. At tsaka, since kailangan rin po natin itong 270/90. So, ito, tandaan po natin itong 270/90 kasi ito ang highest motor, which is pare-parehas lang naman. Kaya, ayun na rin yung mamili na lang po tayo. So, yun. So, paano ang naging calculation sa branch circuit breaker computation ng PP3A panel? So, kita naman natin doon. 108.36 kVA, 400 volts, 3 poles. So, pagkuha naman ng current demand load is equals to 108,360 multiply to 0.85 divide 400 square root of 3. So, ang 0.85 yan ang demand factor. And bakit may square root of 3 palagi? Kasi 3-phase. So, makakuha tayo dito ng 133 amperes. So, to get the circuit breaker size, so, itong current demand load plus highest ampere in a motor times 1.5. So, di ba nga kanina ang highest motor is nasa 270/90 VA. So, divide natin sa 400 square root of 3, makakuha tayo ng 39.3 amperes doon. So, ito po, 133 amperes plus 39.3 times 1.5 equals to 192. Since 192 ang nakuha natin sa calculations, so gagamitin nating circuit breaker is yung 225 ampere trip, 225 ampere frame, 3 poles, 400 volts, molded case circuit breaker. Next is the LVSG1. So, I would like to highlight is itong part na to ulit, yung total connected load. Siyempre, ang ating 400 volts and the diversity factor, which is the 1.4, which is indicated here. So, proceed na tayo. So, ang LVSG1 ay may 3,207.459 kVA, 400 volts, 3 poles. So, pagkuha ng current demand load is equals to 3,207,459 multiply sa 0.7 divide into 1.4 times 400 square root of 3. So, ang 0.7 is the demand factor and 1.4 is that diversity factor. So, ang demand factor is always less than or equal to 1. So, ang demand factor is maximum demand all over total connected loads. So, ang diversity factor naman is always greater than or equal to 1. So, basically, yun yung extended version ng demand factor. It deals with maximum demand of different units at a time over maximum demand of the entire system. So, ayun. So, since high-rise rin tong gamit natin, so, 1.4 ang gamit nating diversity factor, which is makakuha tayo ng 2,314.8 amperes. So, sabi dito, pump to panel and capacitor bank excluded in computation na may 1.4 diversity factor. So, for circuit breaker size, itong current demand load, i-multiply natin sa 1.25. So, bakit need natin i-multiply sa 1.25? So, yung additional 25% is for the protection ng circuit breaker. So, ayun, 2314.8 times 1.25, ang makuha natin is 2893.5 amperes. So, papalo siya dito, nagagamit tayo ng circuit breaker na may 3,000 ampere trip, 3,000 ampere frame, 3 poles, 400 volts, and molded case circuit breaker again. So, ngayon naman ay ang LVSG2. So, gaya kanina, total connected load. Siyempre, ang ating 400 volts again. And the diversity factor, which is 1.4 ulit. So, ating computation, may 3,206.532 kVA, 400 volts, and 3 poles. So, for current demand load, equals to 32,06532 multiply to 0.7, which is the demand factor, divide to 1.4, which is the diversity factor, times 400 square root of 3, which is ito ang ating volts, tapos square root of 3. So, makakuha tayo dito ng 2,314.1 amperes. Kagaya kanina, capacitor bank excluded in computation with 1.4 diversity factor. So, para makuha ulit po natin ang ating circuit breaker size, so, ang formula is current demand load times 1.25. So, bakit nga ulit may 1.25? Kasi, ang additional 25% is for the protection ng circuit breaker. So, 2314.1 times 1.25 is 2,892.63 amperes, which is gagamit tayo ng 3,000 ampere trip, 3,000 ampere frame, 3 poles, 400 volts, molded case circuit breaker again. Okay, so next naman is for the LPR panel. So, nakikita ba ito ang total connected load, which is 28070 at ito 400 o 230. Ayan. Okay, next. So, ayan. For the LPR, mayroon siyang 28.07 kVA, 400 volts, 3 poles. So, para makuha ang current demand load, gagamit tayo dito ng 28070 divide 400 square root of 3 equals to 40.5. So, it doesn't require a demand factor now. So, for the circuit breaker size, current demand load times 1.25 again. So, 40.5 times 1.25 is equals to 50.63, which is, gagamitin natin is yung 60 ampere trip, tapos may 100 ampere frame, tapos 3 pole, 400 volts, molded case circuit breaker, which is indicated rin naman sa schedule of load. Okay? For the panel DPB naman tayo. So, ito is yung 875805. Highlight lang ulit natin. And the voltage is 400 volts. Ayan lang. So, let's proceed. For the DPB panel, meron naman tayong 87.805 kVA, 400 volts, 3 pole. So, for the current demand load, ang formula is 87805.75 times 0.75 over 400 square root of 3, which is meron na ulit tayong demand factor na 0.75, which is ito yung full load current at 75 demand factor. So, makakuha tayo dito ng 948 amperes. So, to get the circuit breaker size, ang formula naman natin ulit is yung current demand load times 1.25. So, 948 times 1.25, makakuha tayo ng 1,185 amperes. So, kaya gagamit tayo dito ng 1,200 ampere trip, 2,000 ampere frame, 3 poles, 400 volts, molded case circuit breaker. So, makikita rin natin yan na yan yung ginamit sa schedule of loads natin, which is nag-satisfy naman. So, ito naman is the LP3A. So, makikita natin yung schedule of loads. May continuation yan. So, highlight ko lang itong 400 volts and 230 volts. Yan. Then, itong total connected loads. 20365. Okay. Let's proceed. So, for LP3A panel naman, meron naman tayong 20.365 kVA, tapos 400 volts, 3 poles. So, pagkuha naman natin ng current demand load is 20,365 over 400 square root of 3, which doesn't require a demand factor again, equals to 29.39 amperes. To get the circuit breaker size, ang formula natin is yung current demand load times 1.25. So, ang pagkuha ng, kaya may 1.25 ulit, sa kadahilan na ang additional 25% is for the protection of the circuit breaker. So, 29.39 multiplied to 1.25 equals to 36.74 amperes. So, dito gagamit tayo ng 60 ampere trip, 100 ampere frame, 3 poles, 400 volts MCCB, which is molded case circuit breaker. So, ito ang indicated sa ating schedule of loads. So, ito naman is the summary. Kumbaga, ito yung ating summary ng circuit breaker determination. So, ayan. Makikita natin yung AHU, 27090, 27090, 27090, tapos ang voltage is 400 volts, tapos ang load ampere is 97.76, lahat-lahat sila. Poles nila ay 3, ang ampere trip nila is 100, and the ampere frame is 100. Mayroon total connected load which is 108,360, which magsasatisfy sa kanina nating tinakel. So, ang next is yung demand load which is 132.95. Kagaya nga dun sa tinakel natin kanina. Tapos, ang makukuha nating ampere trip, ampere frame sa ganong total connected loads is 225 to 25. Which is nagsatisfy naman dun sa calculation natin kanina. It's a good sign. Ang summary naman na to is yung sa LVSG1. So, nagkaroon ng total connected load. Ito, katulad ng sinasabi ko kanina, which is 320.7459. And the voltage all throughout doon is ay 400 volts. Ayan, kita naman. And, ayan na nga is yung, for the total connected loads, ang magagamit nating circuit breaker is that 3,000 circuit breaker and 3,000 ampere frame. Why? Because ito ang nakuha nating demand load kanina, which is the 2,314.85 amperes. Yan yung current natin. So, bale, nag-satisfy na naman. Ito. Tapos ito yung, yan. Ito yung total, which is, ito yung demand load. Tapos ito yung total na para masatisfy yung natin, circuit breaker rating. Here is the LVSG2. Ang summary na naman po ng ating LVSG2. So, ito ang ating total connected load, which is ang hinighlight ko kanina, 3206532. Ang nakuha nating current demand load is the 2314.2. Siyempre, 400 volts all throughout yan. Tapos, ito ang meron ng kasamang circuit breaker protection, which is naka 1.25. Yan. Kaya ang gagamitin natin dito ay 3,000 ampere trip and 3,000 ampere frame. Which is, yun nga, na-calculate natin. So, for the LPR panel, ito naman ang kanyang summary. Meron tayong 28070 total connected loads. Then, nakakuha tayo ng current na 40.52, which is current demand load. Tapos, nakakuha tayo ng kasama na yung circuit breaker protection dito. So, 50.65. Kaya nag-come up tayo sa 60 ampere trip na circuit breaker and the 100 ampere frame circuit breaker. Ayan. Ito ulit ang summary ng ating DPB panel naman po. So, meron tayong total connected load which is 875805. Nakakuha tayo dito kanina, di ba, ng current load na 948.11. Tapos, ito na yung may kasamang circuit breaker protection, 1185.14. Kaya nag-come up tayo sa 1,200 ampere trip and 2,000 ampere frame na circuit breaker. So, ito lang naman yung mga values kanina for the LP3A. So, ayan, yung bawat circuit values. Ito ang total connected loads ng lahat-lahat na yan, which is 20,365. And nakakuha tayo kanina ng current demand load, which is 29.4. Then, yung may kasamang circuit breaker protection sa calculation, which is 36.74. Kaya nag-come up tayo sa 60 ampere trip and 100 ampere frame na circuit breaker. So, basically, ayun lang po yung part ko, which is the circuit breaker rating determination. At itutuloy ng aking partner, next topic po namin, which is the arc flash analysis and calculations. Ayun lang po. Salamat.
Now let's move on to the topic of arc flash analysis and calculations. First, let's start from the definition. An arc flash occurs when an electric current flashes over and travels from one conductor to another or to ground instead of following its intended path. And arc faults are typically only present in systems with a bus voltage greater than 120 volts. Normally, an arc cannot be sustained at lower voltage levels. Similar to the arc formed during electric welding, an arc fault must be manually initiated by an event that establishes a path of conduction or by a failure, such as a breakdown in insulation. Picture of distance from arc flash source. So, ibig sabihin kapag mas red, mas delikado yung pwedeng maging damage niyan sa gagawa ng equipment natin. Kapag sa gitna, moderate, tapos dito, slight, tapos medyo mas space or mas safe siya pag nandito sa area ito. And now, let's go to arc fault current formula. So, this is the formula for arcing current or arcing fault current. In under 1 kilovolt system, the formula for log IA is this one. For over 1 kilovolt system, the formula for log IA is this one. Where log is the log 10, IA is the arcing fault current. It should be in kiloampere unit. In the value K is negative 0.153 for open configuration, negative 0.097 for box configuration. The short circuit current must be in 3-phase volts, symmetrical RMS, it should be in kiloampere, or voltage fault current. The V is the system voltage. G is the gap between conductor. It should be in millimeter unit. So this is the factors for equipment and voltage classes. This is the system voltage. This is the equipment types. This is the gap. This is the gap between conductors. This is the distance X factor. So this one, we can use that in the formula in the further slides, and also this one. So incident energy formula, the formula for incident energy En is this one, where log En is this one, the formula for log En is this one. Incident energy E for system voltage under 15 kilovolt system, the formula to be used is this one. For system voltage over 15 kilovolt system, the formula to be used is this one. En is incident energy. CF is calculation factor, where 1.5 for 1 kilovolt. If it's less, above 1 kilovolt, the CF or calculation factor is 1. D is the working distance from arc source. It must be in millimeter unit. T is the arcing fault duration. It should be in seconds unit. X is the distance exponent that can be seen in the further slide, in the previous slides rather. Arc flash protection distance formula. So the B is the distance from of the boundary from RC point in millimeter. For system voltage under 15 kilovolt, this is the formula to be used. For over 15 kilovolts, this is the formula to be used. EV should be in joules per square centimeter. For example, 5 joules per square centimeter. So hazard risk category matrix, this is the minimum incident energy to its maximum value, and risk category, the minimum rating for of PPE. Now this is the recommended personal protective equipment, in short PPE. This is the risk category. This is the corresponding PPE to be used in said risk category values. Now let's go to our flush calculation. Our group task is to solve for transformer 2, which is LBSG2, or low voltage switch gear 2. In branch circuit number 1, we have RFCJB. In first step, we determine the voltage fault current or short circuit fault current. Our short circuit fault current is 44.234 kiloampere. In next step, we determine the arc fault current or arcing current. This is the formula to be used. And this one, this is the variables. G in millimeter is 32 millimeter. K equals to negative 0.153. K1, negative 0.555. K2, negative 0.113. Factor is 1.5. Our arcing time in seconds is 0.032 seconds. The distance is 457 in millimeter. Our distance exponent or X is 1.473. Our system voltage is 0.4 kilovolts. Now we substitute the variables to the formula. We have the result of 1.19972. Substitute this value to the previous formula, which is this one. We have 10 raised to 1.19972 is our arcing current is 15.84 kiloampere. Next step, we determine the incident energy En. So this is the formula. The formula for log En is this one. Substituting the variables, we have 0.66414. Substitute this to the previous formula, which is this one. 10 raised to 0.66414 is 4.665 joule per square centimeter, or 1.115 calorie per square centimeter. In step 4, we determine the incident energy E at working distance. So this is the formula. Substituting the variables again, we have the final result of 7.168 joule per square centimeter or 1.713 calorie per square centimeter. In step 5, we determine the arc flash boundary dB in millimeter. The value of EV is 5 millimeter. So this is the formula for dB. Substituting the variables we already have, we have the final answer of 583.589 millimeter. Oh, for circuit number 2, RMC3B, our first step is to determine the voltage fault current or short circuit fault current, which is 36.787 kiloampere. In step 2, we determine the arc fault current. So this is the formula to be used, and this is the variables to be used. Same with the previous one. I substitute the variables. We got 1.13661. Substitute this variable. This is also to the previous formula, which is this one. 10 raised to 1.13661. The RC current equals to 13.697 kiloampere. Our third step is to determine the incident energy En. So this is the formula. The formula for the En is this one. Substituting the variables again, we get this one. The result is 0.6007. Substituting this value to this one, 10 raised to 0.6007 is 3.987 joule per square centimeter or 0.9529 calorie per square centimeter. In step 4, we determine the incident energy E at working distance. So this is the formula. Substituting the variables to the formula, we get this one. The result of this formula is 6.126 joule per square centimeter or 1.46 calorie per square centimeter. In step 5, we determine the arc flash boundary dB in millimeter, and the value of EV is 5 millimeters. So this is the formula. And now we substitute the variables. So this is this one. The final answer is 524.5696. In branch circuit number 3, we have MCC or motor control center. In step 1, we determine the voltage fault current or short circuit fault current, which is 35.206 kiloampere. In step 2, we determine the arc fault current or arcing current. The formula to be used is this one and this one. The variables to be used in this calculation is this one. Same with earlier. So now we substitute the variables to the formula, which is this one. The result of this one is 1.12158. Substituting this to the previous formula, which is this one, 10 raised to 1.12158, we got the arcing current of 13.231 kiloampere. In step 3, we determine the incident energy En. So this is the formula. The formula for log En is this one. Substituting the variables, this is the formula. Now, the answer to this formula is 0.584. Substituting this value to this one, which is 10 raised to 0.584. The answer to that is 3.84 joule per square centimeter or 0.918 calorie per square centimeter. In step 4, we determine the incident energy E at working distance. This is the formula to be used. Substituting the variables again, we got 5.9 joule per square centimeter or 1.41 calorie per square centimeter. In step 5, we determine the arc flash boundary dB in millimeter. The value of EB is 5 millimeter. This is the formula to be used. Substituting the variables again to the formula, we got 511.36 millimeter. Now let's move to the last branch circuit number, which is number 4, RMC2B. In step 1, we determine the voltage fault current or short circuit fault current, which is 25.574 kA. In step 2, we determine the arc fault current or the arcing current. This is the formula to be used, and this one, this is the variables. Substituting the variables to the formula, which is this one, the result of that is 1.01216. Substituting this value to this, 10 raised to 1.01216. Our arcing current is 10.284 kiloampere. In step 3, we determine the incident energy En. So this is the formula. The formula of log En is this one. Substituting the variables, which is the one. The result is 0.466. Substituting this value to this one, which is this one. 10 raised to 0.466 is 2.925 joule per square centimeter or 0.699 calorie per square centimeter. In step 4, we determine the incident energy E at working distance. So this is the formula. Substituting the variables again, we got 4.49 joule per square centimeter or 1.07 calorie per square centimeter. In step 5, we determine the arc flash boundary, dB in millimeter. The value of EV is 5 millimeter. So this is the formula again. Now we substitute the variables in said formula. The result of that is 425.088 millimeter. So this is the summary of arc flash computation in low voltage switch to 2. So this is the loads. This is the short circuit current. This is their arcing current, the incident energy, the arc flash boundary, the PPE class required. This is the type of circuit breakers to use. This is the RC time, and this is the circuit breaker CAIC rating. So this is the group member of group 4. I am Grayson Joshua S. Puna, the group leader. My members are Jidan Paul T. Alibosa, Shane Benedict D. Barbosa, Arwin Joseph Garcia, Kathleen M. Lonyosa, Jasmine M. Quinto, Luis Antonio R. Reyes, and Joyce Ann A. Veranga. Thank you.